My plan is first to introduce the topic by asking a question. Does total cholesterol cause heart disease? And then I will introduce interventionism to define and estimate to show how to use interventionism to estimate causal effects. And then the main issue I'm going to address is when are interventions and causal variables well defined? I will rely on case studies to discuss this question. Okay, so suppose we have two groups of patients, one group with a high level of total cholesterol and the other with a middle level. The first group ends up being 20% less likely to develop heart disease than the second. Assume the sample is representative and association between the two variables is not due to any common cause. Does this support the causal conclusion that TC is a cause of HD? No, the association here cannot be given a causal interpretation. Here is the reason. As we know, total cholesterol is composed of HDL and LDL. These two components have quite different effects on HD. HDL has a positive effects on heart disease, but LDL has a negative effect on HD. Now, suppose we intervene to change a patient's level of total cholesterol from high to middle. Will the patient be more likely or less likely to develop heart disease? This result is unpredictable because we don't know the corresponding levels of HDL and LDL. For example, if the middle level of total cholesterol is composed of high level of HDL and the low level of LDL, this has a different effect from the case in which the middle level of TC is composed of low level of HDL and high level of LDL. So unless we know the specific levels of HDL and LDL, we are not going to predict the effect of this intervention. This is the reason why total cholesterol is misleading in causal inference, because interventions on this variable have unpredictable or ambiguous effects on HD. So HDL and LDL should be the cause of HD rather than TC. Now, a more general question is, how do we tell whether a causal variable is good or bad? I will confine my discussion to an interventionist account of causation. So according to this account, there is a crucial link between intervention and causation, which says that X causes Y means that if we were to intervene on X to set X to different values, then Y's value or its probability distribution will be changed accordingly. I hope this idea is very intuitive. Here, the emphasis on intervention means that pure observation is not enough for defining causation. Interventions are needed to distinguish causation from spurious association. And of course, it's very important that these interventions need to be well defined, as I will discuss later. However, in causal inference, we often care about how big causal effect is. Interventionism can be used to define the size of a causal effect. Here is the definition. Consider two variables, X and Y, describing a certain system or individual. The effect of X on Y can be defined in terms of how manipulating X value changes Y's probability distribution. And in other words, it means the effect is the association between X and Y when X is intervened on. Also, put differently, the effect is the difference in Y's probability of achieving a certain value when X is set to different values by interventions. Let's consider a simple case. For example, if X and Y are binary variables with values 0 and 1, The causal effect of X on Y can be understood in this way. Suppose X is changed from equal to 1 to equal to 0 by interventions. In this case,
okay, now suppose X and Y are binary variables with values 0 and 1. Now the causal effect of X on Y can be measured as the difference between these two probabilities. So first, we set the value of X to 1 by an intervention, and then set the value of X to 0 by an intervention. The effect of X on Y would be the difference of the conditional probabilities of Y equal to 1. Okay, so how to estimate causal effects? Typically, we rely on experiments or observations, and the estimation has to be done at the population level. So first, how to estimate causal effects from experiments. Suppose we want to infer the effect of a new drug on some disease. To estimate the effect, we assign drug and no drug to two similar or homogeneous groups of individuals. And this is the similarity condition often achieved through randomization. And then we compare the rates of recovery in the two groups. However, experiments are not always available. Without doing any experiments, suppose we observe a strong association between X and Y. Can this observation tell us anything about the effect of X on Y? The key is to consider hypothetical interventions. To know the true effect, we need to infer from the observations, and also often this is combined with background causal knowledge, what the association between X and Y would be had X been intervened upon. It can be shown when background causal knowledge is sufficient, we can infer the true effect of X on Y by controlling for certain variables. Let's look at a simple example. Suppose we know X and Y only have one common cause, C. The true effect of X on Y will be identical to the association between X and Y after we control for C in the observational data. After controlling for C, it would be as if our data were collected from a controlled experiment in which we assign X equals to 1 and X equals to 0 to two otherwise similar groups. Okay, now the main issue is how to understand well-defined interventions and well-defined causal variables. In causal inference, we need to choose a set of causal variables to represent a causal structure. And of course, there is a question of whether the causal variable choice is good or not. And typically, whether X is a good or bad causal variable is context dependent. However, there are some variables that seem to be problematic in a very large range of important causal inquiries. And an important reason why some causal variables are bad is that they cannot support well-defined interventions. This is to say, X is not a well-defined causal variable with respect to Y if there is no well-defined interventions on X with respect to Y. This is a direct consequence of interventionism, because interventionism says that a causal claim like X causes Y should be makes sense only if there are well-defined interventions on X. However, it's quite difficult to provide a general criteria for well-defined interventions, since interventions may take various forms. But there are some purported general criteria, and these criteria I think have some limitations. The first one is proposed by Holland and other causal inference practitioners. They restrict well-defined interventions to interventions on what treatment an individual receives. For example, those interventions on drugs in randomized controlled trials would be well-defined interventions. However, this criteria is very restricted. This throws out a lot of variables that intuitively support a causal interpretation. I won't discuss this further because it has been objected by many people. Another popular proposal requires that an intervention is well defined if and only if the effect of the intervention on some variable X should be unambiguous or consistent. However, all interventions in special sciences are in some sense and somehow ambiguous. So the more important question is the specific nature of the ambiguity, namely whether the ambiguity leads us to abandon X, like in the case of total cholesterol, or it just means we should be more cautious in using X without abandoning it. Therefore, instead of looking for a general criteria for well-defined interventions, I will study some representative cases. Recall in the beginning, I said that interventions on total cholesterol with respect to heart disease are ambiguous. This means we should not treat total cholesterol as a cause of HD. Note that it makes no sense to eliminate the ambiguity by controlling for some variables like HDL. Because if we could control for HDL, then we already know the specific levels of HDL and LDL, and then why don't we just use HDL and LDL as causes of HD? And also, it's important to note that because TC has a logical relationship with HDL and LDL, for this reason, these three variables shouldn't be included in the same standard causal graphs. However, there are other kinds of interventions that may seem to be ambiguous. Consider the following intervention I on X with respect to Y. So this means we want to use this intervention to detect the causal effect of X on Y. However, this intervention is fan-headed because when this intervention variable, sets X to a certain value, it also affects Y through a causal path that doesn't go through X. So this is not a perfect intervention because the association we observe between X and Y under the intervention is not the true effect of X on Y, because the intervention itself introduces spurious association between X and Y, as this variable serves as a common cause or confounding factor. And this basically is the same structure. However, even if most interventions on X are fan-headed, it doesn't directly imply that we should stop using X as a causal variable. Why? Because it's still possible to estimate the true effect from intervention if we know the direct effect of I on Y in this case, or we could control for Z in the second case. In this case, the spurious association introduced by variable I could be eliminated. And also there is another reason those fat-headed interventions doesn't imply that we should stop using X as a causal variable, is that there may be non-fat-headed interventions on X such that they can reveal the true effect of X on Y, although it has to be admitted that maybe in practice, they cannot yet be used to estimate the effect. And now I will show interventions on obesity fat-headed in this sense. It has been argued by Hernan and Topman that obesity doesn't support well-defined interventions, so the effect of obesity on mortality is ambiguous or inconsistent. Their arguments are complicated, but the arguments can be divided into two parts. First, in experimental studies, different interventions to eliminate somebody's obesity, for example, through exercise or through diet control, will lead to significantly different mortality outcomes because if you eliminate somebody's obesity through exercise, this will have this person will be less likely to die in 10 years, for example. Both exercise and diet control are fat-headed interventions. They will affect mortality through a causal path that don't go through obesity. The causal structure is basically like this one. So even if you carry out a randomized controlled experiment to intervene on obesity, the experiments themselves will not straightforwardly tell you what the effect of obesity on mortality is. And in observational studies, the problem is more complicated. Here, when we compare the mortality of two groups of people with and without obesity, the implied hypothetical intervention is also fat-headed. The reason is that obesity is a result of complicated determinants, for example, diet, exercise, genes, illness, etc. The implied hypothetical intervention is to assign obesity and non-obesity to two groups of people by changing these determinants. This intervention can affect mortality through other causal paths. However, although interventions on obesity seems to be ambiguous, the ambiguity is at least eliminable in some cases. We still have good reason to use obesity as a causal variable. And why we want to keep this variable, obesity, because this variable supports more general causal conclusions such as obesity affects mortality, in addition to more specific causal claims like diet affects mortality, exercise affects mortality, etc. So now how to eliminate the ambiguity. In experimental studies, we can still estimate the true effect of obesity as long as we can deduct the direct effect of interventions on mortality along this causal path. For example, there may be available data about the effect of exercise on mortality when obesity is controlled. In observational studies, it's difficult to eliminate the direct effects of those determinants of obesity on mortality because there may be unknown genetic determinants of obesity that also affects mortality. But we may have observational data that are as is generated from controlled experiments. For example, we may compare two groups of obese people who kept similar body weight during their early life, which indicates that they have similar genetic determinants. But later, the first group reduced their body weight through exercise. Basically, it just tried to find a case in which this effect of determinants on mortality can somehow be eliminated. And then we can estimate the effect of obesity on mortality through this causal path. Okay, now another even more complicated case, race. Race involves biological, psychological, social, and cultural characteristics. These characteristics constitute one's identity and life experience. It's not straightforward what it means to manipulate one's race. This is why Holland says, because I'm a white person, it would be close to ridiculous to ask what would have happened to me had I been black. But I will argue at least sometimes we can and need to use race in causal inference. My argument has two parts. First, it's possible to have observational data about race that are at least generated from controlled experiments. And secondly, race cannot be replaced by perceptions of race in causal inference. Before I go on, it's important to note that when I say race causes income, this doesn't mean one's race directly influence one's income. At least for examples I will discuss here, the effect of race is entirely mediated by perceptions of race. Namely, we can say race causes perceptions of race and then causes income, but there is no direct causal relation from race to income. And as we will see, this doesn't mean race could be replaced by perceptions of race in causal inference. There is already a controlled experiment argument for race as a cause by a philosopher. The argument says, imagine that in a society there are two racial groups, black and white. All the units in the population are perfectly homogeneous regarding any other possible causes of wages other than race. For example, education, working experience. This means those people are only different with respect to their race. Now, suppose the black people are much less likely to get high wage jobs than the white people. The only cause of this wage gap is race, because all the other factors are controlled. This argument does show in this scenario that race is a cause, but it has a significant limitation. That is, in a realistic society, the population is not homogeneous with respect to, for example, education. If we want to apply this argument to a realistic society, we only consider the effect of race on wages when this variable is controlled for. So we only consider the effect of race on wages through this path. However, we may also care about the effect of race on wages along another causal path, depending on what we are concerned with. Now, to make this idea more concrete, consider the following hypothetical job application results from a company. Among all the job applicants, black applicants are 20% less likely to get high wage jobs than white applicants. This means black applicants are at at a disadvantage overall. However, when we compare those black and white job applicants with very similar education background, etc., it turns out black applicants are 5% more likely to get a high wage job than the white applicants. So this indicates that the company slightly favors black applicants, despite that overall black applicants seem to be at a disadvantage. So this implies that there is a deeper racial inequality, which are beyond the control of the company. However, can we interpret the result in A as showing that race is a cause of education and therefore a cause of wages? We can interpret the data causally if we can show them that data are as if generated from a controlled experiment in which black and white job applicants grew up in families which have similar socio-economic status and education, culture, background, etc. And they grew up in cities with similar available education resource, and so on. Intuitively, this controlled experiment can tell us the accumulative influence of one's race on one's education since they were born. Of course, such observational data may be rare, but even when confounding is not properly controlled, if we find that race is highly associated with education, which can hardly be given an alternative explanation, it still indicates a potential racial problem. Now, you might be wondering if I say the effects of race are entirely mediated by perceptions of race, why don't we just replace race with its perceptions? To see why this won't work, we first replace race with perceptions of race. Here. So, however, the new color graph will not work because the perceptions of race that affects wages through this path belong to the employer of the company. It's the employer's perceptions of the applicant's race that causes wages along this path. But the perceptions of race that affects education belong to other people. We shouldn't combine them into one variable because apparently the employer's perceptions doesn't affect the job applicant's education background. However, now we may think that we could use two different variables to replace race, PR and PR star. The following graph is also wrong because it suggests that PR and PR star should be statistically independent, and apparently this is not true. Because if you perceive, if the employer perceives an applicant as black, then the same employer is also more likely to be perceived as black here. So actually, this is because there is a hidden common cause race. This is why we cannot replace race with perceptions of race. And we end up with this color graph. And often for convenience, we omit these two variables, PR and PR star. And we go back to the original color graph. Okay, conclusion, part one. as we see, some variables can bring trouble for causal inference when used carelessly. However, even if a variable may bring trouble sometimes, the question remains whether it should be replaced, as in the case of total cholesterol, or it's still useful, but we must be cautious in using it, such as obesity and race. In the cases I have discussed, it's not a good idea to replace obesity with exercise or diet, or to replace race with its perceptions. And I think these case studies may provide templates for considerations on other variables. I didn't give a general definition of well-defined interventions, but the following points may be of some general importance. Interventions can take various forms, and causal graphs are often useful in analyzing them. The second point is that whether X supports well-defined interventions should be considered with respect to another variable, Y, or be considered along a certain causal path we are interested in. This is suggested in the case of race, for example. We should consider interventions on race with respect to education and interventions on race with respect to wages. These two kinds of interventions should be considered separately. The idea of controlled experiment is useful because if it's possible to design a reasonable controlled experiment to test the effect of X on Y, an intervention on X with respect to Y is also well defined. And thank you.